So today we're going to talk about how to access data in a factory that's currently give a factory access to data when they're currently using paper for their processes. How we take the journey from using paper and pen to applying to do a simple application with machine learning. So we will start presenting who is T2C. Then we'll review what's the current factory status. We'll show simple digitalization of an industrial process that already allows us to start collecting data and show them that they can easily improve their processes. Then we'll automate with the data collected warehouse system and collect again more data. And finally, with all those steps, we'll be able to solve a simple use case with machine learning. So who is T2C? Well, T2C was founded in 2003 in Barcelona, and our main values are talent, consistency, efficiency, and innovation. We currently have offices in Barcelona and Malaga since October 2018. These values are always applied through 4 main areas: SAP, business intelligence, IT systems, and development. And since we had business knowledge from SAP and business intelligence areas, architecture knowledge from IT systems, and we could build applications to consume models, in January 2018, it seemed the normal step to open a new area called advanced analytics that is transversal and uses the knowledge of all the other areas. Let me get some water, please. Okay, so how many of you have factories in your companies? Anyone? Would you say they're early adopters with technology? They get the technology fast as soon as it's out of it? Okay. Okay. Okay, so you rely on consistency because it's operation and there's a lot of money into that. So we always see the same graphs about Industry 4.0. There's additive manufacturing to produce simulations of products or to build pieces to fix the machines. There's autonomous robots that we will see a project on autonomous robots today, in fact. There's IoT, but all this buzz is not directly applicable to a factory. You have to take certain steps before, and that's what we're going to review today. So don't push me. I'll only say that the company where we did that is a yogurt company, and I won't say anything, so please don't ask. The guess is on you. And when we arrived there, they were using papers and printing, pens. They were doing manual checks. For instance, to check the pressure of a container, they would go there, pick a paper, and note it with a pen. And this provides them low traceability because the time is not registered, the measures are not always understandable. So it's not a valid process to have a data-driven strategy in a factory. And also, they based their processes in average measures. For instance, when producing, they were basing the times to do the production planning on average measures, which is not optimal, to say something. But the other rule is, if ain't broke, don't touch it. They rely a lot on consistency. So our first objective is to break the wall. Our first objective is breaking the wall, so we could tell them that manufacturers' adoption of machine learning to improve predictive maintenance should increase at 38% in the next 5 years. And that's according to PricewaterhouseCoopers. It's not me who's saying it. But again, do you know the answer to that? If ain't broke, don't touch it. That's the answer. So we took a different strategy. We started telling them, we told them that without data, they were going blind. They were having some ideas by transcripting the papers to Excel and doing average measures and some graphs, but they weren't really analyzing their data because they didn't have proper data, and the quality of the data was not good. So we started a process we digitalized the picking process in the production line, and this allowed us to start gathering data in a structured format with the proper fields. So what we did here is something really simple, believe me. They were checking the production plan from a printed paper in the morning. Then they'll check the code in the bill of materials or the recipe directly with the code bar in the product. And if there's an alternative material, they would receive a call and with a pen, change it in the production plan. That's really ineffective, and if someone loses the paper and needs a reprint, he loses that information. So what we did is to build a web in 3 weeks, more or less, I think it took, to upload photographs of the materials. This allowed them to visually check if the material they were putting in the line was correct. They also could check with a barcode reader the product and be sure that it was matching the bill of materials. And the alternative materials were defined by the administrator, and they received it in real time. That's a pretty easy application, nothing too strange, but this allowed us to create the first database in the factory and to start collecting data from SAP. So we had 1 foot inside to start doing projects with data. So what were the benefits of this simple yet effective project? Well, the picking in the production line was much faster. The production errors were hugely reduced because they could now check with the barcode reader. The traceability on the errors was more granular and correctly registered, because if you're an operator in the line and you make a mistake, would you register it at the perfection? Perhaps you commit some mistake in the hour to say that it was the end of your turn, for instance. This is automatic, so they couldn't do that. And the material waste was reduced because the alternative materials were never missed. It was transparent for them. And overall, we achieved data collection. That was our objective, but they obtained a good benefit along with the project. So once we've gathered data, we need to prove that this data has value. So we built another product on top of that. By the way, the first product was called the Triles. And the next one was Grabit. And what was the objective with Grabit? Well, we wanted to automate material delivery to the line. We have already improved the picking process in the line. Now we wanted to improve the connection with the warehouse. So Grabit will download the production plan directly from SAP, compute the material needs based on that production plan, material quantity and time. Then we'll suggest the line operator a mission, and I want to define a mission now. A mission is a movement with a source and destination, but it's only a movement. But the definition, well, the name is mission in this case, but we will suggest the user a mission to perform based on their needs of his line, and if he accepts it, we will select a package that satisfies this material, this quantity, and in the desired time, and prioritize missions between them. So the warehouse consumption was hugely optimized, and we send this mission to an LGV, a laser guide vehicle, that would serve materials directly to the line, prioritizing the needs of the different lines. And again, this is not machine learning. These are business rules, well, industrial rules, if you allow me. But this is not machine learning. This was the LGV. It's a huge robot because it reaches, I think, that 5-meter height to extract packages. But what I want to stop here because there's several interactions. There's interaction with several systems. We first interact with SAP directly, so we're kind of connecting business and the production line. Uh, we connect to the LGV system. The robots were provided by a third-party company. And we also connect to the production and warehouse systems of the factory because we need to know where are the packages in all moments and where is the current production. We cannot rely only on the production plan. So Grabit would update the position as it moves materials around the factory. And finally, we have a trellis. Remember that first and simple application that communicates the alternative materials to Grabit. And this is the first version. Current version is a bit more sophisticated. We're executing, in fact, the second phase of the project with more functionalities with the client right now. But since it's not finished, I couldn't show it. But we achieved I think it was 3 months of development, we achieved huge benefits. First, the buffering in lines was at last efficient because they used to have to request more packages than the ones that could fit in the buffer of the production line. The delivery errors were drastically reduced, not eliminated because you can have errors in your inventory, for instance. The material management and consumption was more effective because now we were consuming based on those business rules and not based on a man with a truck downloading the package that best fits his needs. And this was an unexpected one. Their budget for shelf repairments or repairs was reduced because now there's a robot accessing the shelves. So they're not broken that often. So we're now perform data gathering. We have proved data value. They are ready for some machine learning. And we're currently in the phase of studying with them what could we do with the available data. Not all processes have been treated like that, so there are different sources of data. But it makes sense to do a brief use case with Grabit, because Grabit not only accumulated data, but also generated data. So let's have a look at the movement data. We have the movements queue, that it's simply a transactional log of all the movements. The movements have several status that are described in the status code table. Then we have the master materials info that provides info about the materials, the master package info that provides, and the master package info that provides info about the package and that relates to the materials info table. So we could do something like this. The line operator requests material. Grabit sets the priority, origin, and destination of this material. A mission is created, and we can predict if there's going to be an error or a success in this mission, and then take actions, obviously. So we have several tables. There are much more tables in the project, but to make it simple, we've only gathered 4 of them. And we create machine learning ready data in a structured way by joining tables and filtering some items. And BigML automatically does the feature engineering on the datetime fields. Thanks for that, by the way. So we finally obtain 5 months of historical data about movements. We only select the finished ones, the finished registers, and 40,000 rows and 44 features. Well, 21 of them are automatically generated datetime features. So did you notice something strange here? There's a little trap. No one? We're trying to predict, remember, if there's an error or not. Do you see any strange field? Error reason. So we missed that in the import and data cleaning. We executed the first model, and one variable had the 100% importance when we computed the importances of the model. So we were committing data leakage, and it's not possible to use this variable also because we won't have the error reason at the moment of predicting because the mission hasn't been executed. So always be careful with data leakage. Once we've avoided committing data leakage, we will define our target variable. So status, there are more values, but we sliced the data set in order to make it simpler. Status has 4 possible values, but if you read the descriptions, 4 is OK, and the others are errors. So why won't we solve a binary classification problem? Let's only find true and falses. Let's make it simpler. And this also helps us to balance our objective because there's more force than any of the other classes. So we will get a more evenly distributed target variable. For this matter, flatline always comes in handy, and it's pretty easy to do the transformation. And to prevent this data leakage, here we remove error reason and status from our features to train the model. So we've created a new target variable and removed some variables. We split our data set into training and testing. I guess you've already seen that today. And we first train an anomaly detector only on our trained data set because it's generally a good idea to remove anomalies to prevent bias when training your model. Imagine a house data set, 1 square feet house that's worth $20 million would be an anomaly that would hugely impact the performance of our model, and we want our model to solve the general cases, not the concrete ones. Well, you can have both objectives, but in this case, we want to be as general as possible. So once we've removed the anomalies that are above 60%, because we want to maintain the distribution, we go on to the next step and create a model. And once this model is created, we evaluate it, and we see that we already got pretty good results. We have a recall over 70% on both cases, true and false, or error and OK. And this could be improved, of course, but we're having pretty good results already. The most important variables, of course, are features, sorry. The most important features are source and destination. But we could, at this point, create predictions and evaluate if a mission is going to be a success or not, or how likely is to be a success or not. And this is predicting, we could be prescripting. So Grabit would create the mission, we would predict it, and when reviewing an error, we could play with the variables in order to create new missions and test if they pass the model tests. I mean, for instance, imagine that I create a mission, the prediction is that it's likely to be an error, and Grabit can then get this feedback and modify, for instance, the source by selecting another package from the same material and retest the mission again. This way, we would possibly reduce the errors committed by the ladder guide vehicles. So, the whole process, we showed them that they needed data to drive. They couldn't be driving with only one eye put into the road. We did a simple project, 3 weeks, not complex one, that has a huge impact in the daily work. The operators were impacted by this directly. They made their life was simpler. Then once we had some data and a database already in the industrial process, we created with a third-party partnership a system that automated the movement from the warehouse to the line, to the production line. And finally, we're ready to do something with this data and to prescript. However, we see machine learning today applied to some specific use cases, but we deeply believe that with tools like BigML, we could spread this across the whole organization. And today we showed an industrial case because it's one of the most difficult to access verticals of a company. Well, I don't know if you agree, but generally it is. And machine learning can solve problems there too. So don't limit yourself. Let's spread the machine learning across the company. Thank you all.